Hello everyone, my name is Lennard and I'm an application engineer for Rigel Medical. In my last webinar and with this electrical safety webinar series, we went through some of the theory, but today we're going to put this into practice and how it applies in real world testing conditions. I'll firstly give a quick overview on our company and also some of the theory, just as a quick refresher for anyone that missed the first webinar. These are important so we can compound some of that information regarding some of the standards, the codes, some of the types of medical equipment, and looking quite rigorously into the applied parts. After that, we'll go on to real-world life application testing, such as testing unique devices and different conditions. And with this, I've got a couple of short pre-recorded demonstration videos which we can run through, which will just show us how to utilize Rigel devices in these situations. Firstly, a little bit about ourselves at Rigel Medical. We are renowned globally as a designer and manufacturer of reliable, portable and compact biomedical test equipment. Our products ensure that critical medical equipment is safe to use throughout the device's life cycle. As metrology specialists for almost 4 decades, our innovative testing solutions have been mitigating risk worldwide in healthcare environments. We've got 2 operating locations. Our main manufacturing site is based in Peterlee in the UK. We've also got a US office based in Tampa, Florida. We've got 7 Rigel authorised global service centres. We're operating in over 110 countries and we've got over 40 distribution partners. Okay, so medical electrical equipment, what is it? It's defined in IEC 60601 as any electrical equipment that is designed for treatment, monitoring or diagnosis of a patient's condition. IEC 60601-1 provides the standardised general requirement for basic safety and essential performance of medical electrical equipment. So this is the international standard. It's used for design, development and production. The other standards are derived from 60601, but they're often with a recurrent testing approach, which we'll come on to. And often this is the reason that these standards and codes are more time saving, and they often exclude some of the destructive type tests that are found in IEC 60601-1. Okay, so some of the standards and codes. The Global Type Test Standard, IEC 60601. We've got ANSI AMI 60601, and this is just derived from the international standards for the USA and Canada. We've got IEC 62353, which is our routine test standard used in Europe, the UK and Europe. NFPA 99 in the USA, so this is routine testing. It's much broader in its application, and so it applies to healthcare environments in general as part of the National Fire Protection Association. And this falls under the 60601 test, so there is relevance between any of these recurrent tests and the ones found in 60601. Also got VDE ODE 751, which is used in Germany, ASNZS 3551, Australia, New Zealand. Again, got this relevance to IEC 60601. Okay, so these 2 standards are internationally recognised medical testing standards. Also, there's IEC 61010, but this is used during design of medical devices, so we don't talk too much about this for this type of application. Testing depends on the stage of a product's life cycle. So in this table, we've got your IEC 60601, your standard is for your type tests. You've got IEC 62353, which is a standard for recurrent testing, and you've also got NFPA 99, which is a code. And it's important to understand that localized codes such as NFPA 99 are law, so compliance is mandatory. Regardless, following IEC standards is always best practice. The table shows how the tests are all interrelated. Our previous webinars got much more detail, and I can provide this to anyone who missed it or just wishes to go over it again. Okay, so what are the benefits of IEC 62353? Well, at Rigel we push for this standard to be implemented. It's the best way to ensure the device is performing safely once it's out into service. So once it passes that test type cycle of production, this is the best way for to ensure your device is performing correctly. It's internationally recognised, tested and test after repair standard, and provides an alternative to 60601 without being destructive. Widely adopted by many countries around the world, provides different methods for anticipated healthcare environment conditions, e.g. secondary earth paths and types of main supply. Here's some of the advantages and disadvantages. Now, these come directly from the 62353 standard, and it just gives you some of the things to consider. So the advantages with direct method is a high accuracy. It's not influenced by the type of switching in the main supply. Measures the true leakage, which is why it's got that high accuracy. And there's things to consider, whereby you might want to use an alternative method. And these methods are alternative and differential. And these are available in the standard, and I will make these slides available, but I won't go through each individual point that's made. The reason for 62353 is it's outside of a laboratory condition, for more applicable for biomedical engineers that are going out into the field, into the hospitals, and carrying out the testing in situ. So it's there to assist engineers in the field. And this is the measurement of leakage currents. It's a flow chart that's found in IEC 62353, and that provides the leakage methods for the most commonly found pieces of equipment. And this is non-permanently installed Class 1 medical electrical equipment. Note that for equipment leakage current based on IEC 60601 can be performed if the criteria follows this path. This is because it's comparable to that of direct leakage that's found in 62353, so there is crossover. So in this standard it is possible that you can still carry out a leakage current test according to IEC 60601, but it gives you the options depending on how your configuration or your mains equipment is configured. Okay, so these schematics are from IEC 62353. On the right hand side we have our earth bond test, which is pretty much the same circuit across all standards that we've just mentioned. Then we've got our leakage tests. Again, you have relatively similar setups across mentioned standards, and the codes we've just gone over, but it's always important to refer back to them. It's not necessarily this configuration. So equipment leakage, if this is a direct measurement, then it's comparable to IEC 60601. The reason I highlight these is it helps to understand how the safety analyzer measures leakages and earth bond, and also how you're going to set things up. And as a quick reference, if you want to look at these schematics for each standard and code, depending on what firmware you've got installed on your device, it will have these schematics available for that specific standard. This is useful for training, or if you're out in the field for a quick guide. Okay, so what is an applied part? Patient connection, single function. Confusion sometimes between these, especially these two, applied part and patient connections. We try and break it down. Well, an applied part is any part of the equipment which is intended or could potentially come into contact with a patient. Patient connections are all the individual physical connections of an applied part whereby current can flow between the device and the patient. So these two, they're important terms to understand, and it will become more apparent when we look at the testing of other devices such as Infusion. So there is a difference between these. It explains it in the best way possible, but in our example it explains it even better. Okay, so a medical device may have multiple functions, so patient connections can be grouped by their single function. Now if you're using an automatic safety analyzer, it takes care of grouping the patient connections. The Rigel 28 Plus, for example, will group the patient connections and single functions automatically, but it's still important to understand for in devices such as patient monitors or defibrillators where you've got multiple single functions. Okay, so a patient monitor is an excellent example. It has multiple single functions and each with their own applied part classifications, such as ECG leads, etc. Another example is a defibrillator, and here we've got two single functions with different classifications. So for a defibrillator, you've got your ECG leads, you also got the defib pads, and they normally have different classifications. And I'll show you a quick example with these defibrillator connections with our Rigel 288 Plus and how it's set up. So we've got a quick demonstration of how we group patient connections together for safety testing using our Rigel 288. So in this case, we're going to be testing a defibrillator. So with a defibrillator, you've sometimes got multiple patient connections under single functions. So we've got our defib paddles here for one single function, and we've got our ECG leads for another single function. Now the 288 groups them automatically. So let's say our defib paddles are BF, defibrillator proof, and our ECG connections are CF, also defibrillator proof. However, in regards to safety testing, B, BF and CF are all that's relevant. The defib proof classification doesn't really apply. So if we go to automatic mode, we'll key in an arbitrary number for our asset ID. We'll keep it for now as IEC 60601, class 1, and we'll go to applied parts, F1. Now automatically it's set up for the highest classification, CF, for all applied parts 1 to 10. But we're going to change it to defib paddles for the first one. So we've got the titles all listed here. This is BF, patient connections 2. And then we'll edit our second, which we'll call ECG. Type of classification, which is CF. Number of patient connections, we've got 5. So there we go, it's automatically set up. We've already got the leads connected, but when we set it up, it will tell us where to place the leads. So BF 1 to 2, defib pads is 1 to 2 on the applied parts box. I won't be able to see it too well, I'll just move that over. So 1 and 2, and then we've got our ECG 3 to 7, 3, 4, 5, 6, 7. Very simple. We tick and then we go through the automatic test procedure. We'll put in our asset variables. I won't go through this now. I have a webinar planned in 2 weeks' time, which will go through the user interface and how to carry out these automatic tests. And we'll also look about how to set up test codes, which is how we set our number of patient connections per device. Okay, so configurations to understand what type of analyzer is best suited to your work processes. Okay, so here's a couple of examples of our manual testers. An advantages of these testers are it has test and fault conditions which can be selected with a single key press. So it provides simple, easy and fast testing. It's fully manually controlled. So here it's ideal for training or just if you have to manually log results as part of your PM schedule. Some considerations: manual storage of results. There's no automatic procedures obviously, and also there's only patient leakage on the Safe Test 99, and this is USA specific, whereby the patient connections are grouped. So there are limitations, but sometimes this is useful for individuals in laboratory conditions where they're just looking for quick ways of testing, but it is used extensively by clinical engineers, particularly in the USA, where there's a few manual tests that need to be performed and it's much quicker. However, automatic testers are often needed. This is because they have built-in electronic data storage, flexible user definable test routines, so automatic test sequences, direct printing via Bluetooth connectivity, so your pass-fail labels, most commonly used printed. You can also print results. Also compatibility with an asset management system. For the Rigel range, we have Rigel Medibase, which downloads your results and you can produce reports. But it's also capable of just outputting CSVs from the device itself, so CSV or TXT files with the listed results to the asset IDs, and then it can be integrated into the asset management system as you wish. There's also, we'll come on to this in the Rigel 288 webinar, but we've also got a 288 downloader app, and this is Android based. What it does is it converts the test results into a PDF style report, and then you can attach that to your work schedule, part of your asset management system. So really it's for recording results, automating procedures, and making your workflow better. So the considerations: automatic safety analyzers, they do include manual test mode. So if you want to do manual tests, you can still carry that out with an automatic tester. That option is there. It's the most comprehensive, but obviously where you've got menu settings for your test sequences, downloads, can be a little bit more convoluted for a technician to use. So manual testers may be better for less experienced technicians or training. Again, it really depends on your work processes, what the benefits are and disadvantages of each. Now with the automatic safety analyzers, many include semi-automatic modes like the Rigel 288 Plus. This allows for manual control of power up and power down of the device under test, as well as controlling the test sequences. This ensures that correct measurements are performed, and it provides sufficient time to power down any device which is sensitive to power breaks, e.g. ultrasound equipment and PC-based medical electrical equipment. And that will become apparent in the next few slides when we talk about how to test ultrasound devices and fixed installation testing. So this is where semi-automatic mode really has its benefits. Case testing in unconventional conditions. Fixed installation and three-phase testing is one example. It's becoming more and more common, especially in regards to medical imaging. You've got your traditional scanners such as CT and MRI. They're commonplace in hospitals, but you've got technologies now that are combining scanners such as your CT SPECT, and these are very large fixed devices and often three-phase to deliver that power that's required. So it's a question that comes up quite often. We'll highlight here. So three-phased equipment is often fixed, wired or fitted with a high current plug and socket, so to an electrical distribution board. Okay, so we're looking at 603.64-7-710 standard, and I'll highlight that why that's important for IEC 62353. Now most safety analyzers are only rated at 230 volts, therefore they cannot power the equipment during the test. It's unusual to find three-phase medical safety testers, and if you do, they're large and cumbersome, so it's not ideal for portability testing as it was with your typical electrical safety analyzers you'll have in your workshop. Because of this, the safety analyzer cannot power the equipment and do the single fault conditions, so they cannot apply single fault conditions because the device is not plugged into the safety analyzer. So open neutral, reverse mains, etc. cannot be performed. Okay, so three-phase equipment can be fixed, installed or permanently bonded to ground through its own structure. We know that the medical devices cannot power up the equipment during the test. A point-to-point earth continuity test can be carried out between the chassis of the devices and a main earth point. So you want to have a common earth point so the earth bond can be measured. And fortunately we've got a how-to video on how this is performed, so I'll just play that now. So first we connect some 4mm test leads that's applied to the two highlighted sockets. So any 4mm earth bond leads can be used due to the fact that the Rigel 288 device has a 0 function. And then what you can do is short the end of those leads together, switch on the analyzer and select the earth bond test. Because you've shorted these leads together, you can then zero them out using the F2 function. And the zero icon will be indicated in the top left once the zero has been performed. And then once that's been carried out, you can then use the two earth bond leads, connect one side to your three-phase or fixed equipment to a conductive exposed connector, and then your other 4mm probe lead, so it's got to be a 4mm connection to the common earth plug on the three-phase distribution board, or at least a plug that's got a common earth with the three-phase equipment. Then you just carry out an earth bond test as normal and record the result. So with this test you can use any custom lead, and as long as you zero that lead, you'll get accurate earth bond readings. Okay, so for earth and enclosure leakage tests, the equipment earth must be disconnected and routed through the analyzer. Leakage currents can be measured through the safety analyzer, provided the leakage current has no alternative path to earth. This is because the safety analyzer measures the leakage current through a 1 kilo ohm body model. So we need to disconnect the earth from the three-phase device and route this to our auxiliary earth socket if using 288+. The safety analyzer must be from a 230 volt supply with a common earth potential, and that's shown in the diagram. Connect everything else up as normal and run the required leakage tests. So it's important to note that this setup can also be used for fixed single phase devices as well. One important note as well, three-phase distribution systems are used as they're more efficient for high power devices such as MRI and CT. They need that power, but obviously because of that power they're considerably more dangerous. In the UK it operates at around just over 400 volts and should only be changed or modified by a fully trained and qualified engineer. So IEC 60601 tests that can be performed: point-to-point earth continuity test, enclosure leakage, patient auxiliary leakage, and patient leakage F-type. If in doubt, or you have no official guidance available, contact the manufacturer of the medical equipment under test. Okay, so IEC 62353. Here we only have to do applied part leakage. IEC 62353 states that for permanently installed medical electrical equipment, measurement of equipment leakage current is not necessary. So you only need to do applied part leakage, and this is in the standard. For permanently installed medical electrical equipment, measurement of equipment leakage is not necessary if the protective measures against electrical shock the supply mains are according to IEC 60364-7-710. And this is a note that's found in IEC 62353. It is assumed that the supply mains meets the requirements of national wiring regulations, e.g. IEC 60364-7-710. Common question in medical safety testing is about battery medical equipment. Class 3 is known as internally powered or externally powered. Externally powered should just be treated as you would Class 1 or Class 2 device, even if it's battery powered. So if it has a mains charger or adapter, it's just tested as you would any other normal test Class 1 device. The power supplies will have a functional earth, not a protective earth. So functional earth has a different purpose other than providing protection against any leakage currents, so for leakage currents to flow and therefore electric shock. It may carry a current during the normal operation of equipment, but it's normally used for things like filtering or used in things like IT equipment. It's not actually a functional earth. Sorry, it's not a protective earth. And this is why earth bomb readings can be as high as 1 ohm. Then we've got internally powered medical electrical equipment. This is any equipment that has no mains charger or adapter. IEC 62353 stipulates AP direct method. And this schematic shows how we can set this up. A earth clip or probe goes onto the enclosure of the device, and then we connect our AP box up as normal. Also, you might be, also it's fully powered, it's powered from the socket. Also, you might be asking, what are the risks with an internally powered device? Well, let's imagine that the conductive parts of the device have come into contact with some other electrical source. Could be via the device, could be via a user, and it could just be providing very low levels of electrical current. But what we need to then realise is that this device has applied parts that could potentially be connected to the patient. So very low levels of current could be flowing to the patient. So this is why this test is quite important for battery powered equipment. Just ensures that if there's any fault conditions where mains or another source is applied, a patient still has a form of protection against electric shock. Okay, again, externally powered medical electrical equipment is just tested as normal for IEC 60601. For internally powered medical electrical equipment, stipulates enclosure leakage only. There is no mention of patient leakage. Internally powered medical electrical equipment is investigated for touch current, but only between parts of the enclosure, not between the enclosure and earth. The 288 Plus can do enclosure leakage tests unpowered. So it's unpowered there for convenience. You can go out into the field without plugging that into the mains to carry out these tests. All it's doing is measuring the leakage between 2 points. But there is further guidance in the manual on these point-to-point leakage tests if you require them. One more thing to note as well is that many internally powered devices may have only one conductive point on the enclosure. So this is a question we've received quite commonly. It's not unusual to find a device that only has one conductive point. If that's the case, then just place the device on aluminium foil, but if in doubt, contact the manufacturer. But that is what's in the guidance for IEC 60601, which I'll come on to shortly. Okay, so testing ultrasound devices, another popular FAQ, one we get quite often. Ultrasound devices can have a variable number of probes, up to 6, and on some models there is a 3-lead ECG option. So for this test, electrical safety is done in 2 parts. First, you test the ultrasound device alone without the probes, and then you test the probes alone. Okay, so the first part of the test, we test the ultrasound alone without the probes, connect the device under test to the Rigel 288 without connecting the probes. And we're going to be running earth bond test, equipment leakage test, alternative, applied part leakage, if an ECG is present, or any other type of applied part that is not the probe. Select a semi-automatic mode and run a test as normal. So very simple, you run the test as normal, you're just disregarding any disregarding any ultrasound transducer probes. In the second part, we test the probes alone. The ultrasound is connected to the analyzer and powered on. All the probes are placed into a plexiglass container filled with 500 ml of a saline solution. The test is applied part current leakage, F-type, up to 3 probes in the saline together at the same time. We do 3 to save time by grouping the patient connections by their single function. Then if we get any failures, we can investigate which probe type is failing by testing each probe individually. If leakage limits are out of spec, test each probe individually to identify the fault. So why do we use saline? Well, it is specified in IEC 60601 that you can use different types of conductive points if you've got insulated applied parts. I'll come on to that. But we try to look at this from the application of ultrasound in the actual setting where the clinician is using ultrasound gel. Obviously, these gels are water-based, they're conductive. Not only that, they're designed to remove air, which is an insulator. So that this is the ultrasound there is to allow ultrasound waves to move into the body from the probe. And that's what the gel is doing. So not only is it making it conductive to the air, to the sound waves, it's also making it conductive to electricity, or potentially conductive. If we'd imagine that perhaps one of these casings or the actual transducer crystal itself has become cracked, then we can assume that gel can get into the ingress and then it becomes part of the circuit, and you've got potential of electric shock to the patient. So we're assuming all worst eventualities. What we're doing with saline, we're just simulating that condition. So replicating what the ultrasound gel is doing, and it's very effective. One thing to note is just to not immerse the probes fully. We're just immersing the probes to a point where we think there will be patient or user contact. It's always important that you don't submerge these fully. Okay, so the duration of the test must be 30 seconds, and that ensures that any saline gets a good contact between our electrode here and any ingresses that you might find within the ultrasound transducer. So yeah, I have to just reiterate that these methods come from manufacturers of ultrasound equipment, but just remember that this stems from the IEC 60601 standard, which we check. So there are sections in this standard that state to either use 0.9% saline solution, so that's 0.9% of saline in distilled water, or foil if an applied part appears to be fully insulated. Okay, so infusion devices is another one we get asked about, been asked about in the past. Patient connections are not always accessible to touch, and this is stated in the standard, and this is very relevant to infusion devices. So we know that any conductive parts of the applied part that come into electrical contact with the patient are patient connections. The standard also states that the given set or needle of an infusion controller is an applied part. Conductive parts of the controller are separated from the potentially conducting fluid column by inadequate insulation of patient connections. So that tells us that the conductive parts of the controller, so on the infusion device, the parts that are touching the given set are your patient connections, not the given set itself. So it's important to know, obviously this is the applied part, and this part, obviously it's not shown on the diagram, but wherever the given set is clamped, that's where your potential patient connections are. If there's a conductive surface there, that's where you want to be testing your applied part leakage, or patient connection leakage, because that's what we're testing. So that's why these terms are very important to understand when it comes to electrical safety. Okay, so in 60601-224, particular requirements for the basic safety and essential performance of infusion pumps and controllers, there's a section there. It states that applied parts of an infusion are type BF or CF, and you only check it by inspection. You check compliance by inspection, because you've checked the electrical conductivity at the controller, and that's where your potential patient leakage could occur. Now, I've noticed sometimes on forums there's been a lot of to-ing and fro-ing with what's the correct practice, but always follow the electrical safety standard, and that's what's specified. Okay, so infusion devices, are specified within IEC 60601. But what about other applied parts with fully insulated surfaces? Okay, I elaborated on this slightly already, but this quotes the standard directly. So these applied parts can be tested either enclosed in a conductor such as metal foil. Alternatively, the applied part can be placed in a saline solution where the patient connection is formed by a fluid which contacts the patient. The fluid is replaced by 0.9% saline solution. An electrode is placed in the saline solution, and this electrode is considered as the patient connection for the applied part concerned. So there's two ways. You can either encase it in metal foil, that gives you a conductive surface. I've seen biomed engineers use this for cuffs, BP cuffs, SpO2 probes, etc. And this, of course, was used in the last example, the penultimate example with ultrasound, whereby saline solution is used in exactly what's recommended here. And although we got that from an ultrasound manufacturer, that method, so it is the correct method of testing according to the IEC internationally accepted standards. And that brings us on to the testing summary. Testing correctly is understanding the medical device and the way it's connected. So the ultrasound was a good example of understanding how it's connected, how it works while it's in use, and using that we can find practical and correct ways of safety testing according to the standard. So there's always ways and means of carrying out testing to application. Use common sense and what you can find from the electrical safety standard. They're not there to confuse people, they are there to guide and assist. So decision making should be well informed. Appreciate what you would expect as a value. And this comes obviously from experience. You're looking at trending, what values you're expecting to see. We can compare values with the same type of instrument and also the year-to-year testing values. Also got visual inspection. It's critical to avoid incorrect testing. We know that from the previous webinar we spoke about that 70% of failures are picked up at this stage. So visual inspection is one of the key areas within the application of electrical safety. Testing is not a competition who can pass the most equipment. Safety of devices is what's paramount. Standards provide maximum allowable leakage values. They do not provide typical values. But with common sense and experience, these expected values will just become second nature. Just can't reiterate that common sense is your best tool. Really helps within the field of electrical safety. And that brings us to the end of today's webinar. If anyone's got any questions, please pop them in the question box below. I will make these slides available in the handout section, and I'll also actually just pop the introduction to electrical safety as well, just in case you missed the first webinar. They might be useful to you. I've also put the link for our presentation surveys. If you don't mind filling that out for us, it'll only take a few seconds. It just helps us improve on our presentations. What other unconventional conditions would you like to see as well? So we might have missed some that you feel were really important in the electrical safety and healthcare. So just highlight anything in there, but you could also pop that in the chat box, in the question box below, if there's anything you'd like to see or anything you'd like guidance on. We're here to help with any of these types of unusual conditions you'll find in healthcare. If anyone's got any other questions, as I say, just pop them in the chat box below. But that does bring us to the end of today's presentation. So I'm just going to go through some of your questions and answer them now. Okay, thank you again for viewing this webinar.